Hey everyone, we are looking at some more specific information related to energy and its conservation. These are just 3 things you should know that will help you approach a problem and make sure you're not confused about something if you see this term or if you see something phrased in a way that we haven't so far seen it. All right, it's really just 3 quick things. Let's go over each of them. The first thing is really just the term, all right? And that term is mechanical energy. In this class, mechanical energy is really what we're talking about when we're dealing with energy conservation. And mechanical energy is different from other types. There are types like nuclear energy, energy from heat, energy from light. But here, we're referring to the energy that's associated with an object's motion. Think of kinetic energy. Or its position, like gravity, gravitational potential energy. Okay? So while there are these other types of energy, and to be honest, there's also other types of energy conservation, in this class we're dealing with mechanical energy. You might see that in a textbook problem or on the AP test if they use the word mechanical. Don't freak out, it's nothing new. It's just the type of energy we are dealing with. That's the first one. The second part has to do with energy loss. Our main topic here is the idea that energy isn't lost. The total amount is staying the same before and after. But obviously in real life, energy is not always staying perfectly the same. Even mechanical energy doesn't stay perfectly the same. We saw that with the bowling ball example. All right, the AP test, especially this new one, this test is about 4 years old. They like to see if you understand what's going on if energy isn't being conserved. So if there's a difference between an object's initial and final energy, well, it's pretty obvious. It means that it's not being conserved, and some of that energy is being lost. Why that is important? Remember how we came up with our equation for conservation of energy. We said the net work is equal to the work done by conservative forces plus the work done by non-conservative forces. In order to get our conservation of energy equation, we got rid of this term. We said, let's assume there aren't any non-conservative forces. Well, let's say that's not true. Let's say there are some. Well, if you remember when we do this work net by the work energy theorem, that's delta K. The only work being done by a conservative force that we've looked at so far is the work done by gravity, so that's U sub G, plus some work done by a non-conservative force. If you know the energy before or after, or if you know like the initial and final kinetic energy and or the initial and final gravitational potential energy, the leftover, whatever is lost, whatever isn't there, that must be work done by some non-conservative force. And to be honest, you might even come across a question where it wants you to find the force being done by that lost energy. And you could, because work equals FD. So I've seen problems where energy isn't staying the same. You just got to recognize what that means. And maybe a trickier problem would be if that energy is being lost, what's happening to it? And what's happening to it is, well, there must be some non-conservative force, just like friction, that's doing work. That's why the bowling ball eventually slows down. Okay? Yeah, we have delta K and delta UG, but also the frictional force is doing work. All right? So that's the idea of energy loss. Sometimes energy isn't being conserved. The last one, and maybe the trickiest. All right? We talked about systems when we were doing Newton's law, and we introduced the idea that a system is just what objects you're looking at, whether it's one object or several objects. It plays an important role in energy also. All right, so part C is all about the importance of systems in energy conservation. And I have an example problem to get us started, to get us thinking about it. Let's say we have this car. It's driving on top of a hill or a cliff. That's the best I could do for a cliff. Haha. Obviously, that cliff is some height h above like the ground, surface level, where we might call this h equals 0. And the car is moving, so it has some velocity. Looking at this, we would say like, okay, that car is moving, it has kinetic energy, and it has some height, it has gravitational potential. But we have to be clear. on what our system is. All right, look at this bullet point here. If our system is just the car, that means all we're looking at is the car. We're not looking at anything else. So imagine we zoom in. And if we zoom in, this is all I see. I see the car. I see like the wheels are spinning. You know, it has some velocity. I can see it on the ground. But notice what I don't see. If this is my system, even if I'm zoomed in a little more technically, right? I almost shouldn't even see that part. Ah, there's my system. I don't see the cliff anymore. All I really am looking at is the car. I can still tell the car's moving. I can still see like, oh, okay, it has some kinetic energy. But if I no longer see the cliff, well, how do I approach gravitational potential energy? Well, if I can't see the cliff, it's almost like I can't even see the Earth. And this is important because gravitational potential energy is due to the force that the Earth is applying. It's due to that gravitational force. Gravitational potential energy requires the Earth. All right? Even think of the equation, UG times H. No Earth, no G. So if our system is just the car, that must mean that Earth isn't part of our system. And if that's true, we could not and we should not consider gravitational potential energy. So, and the AP test has had problems like this. If they say the system is just the car, well, if the system is just the object, the only type of energy we know, the only type of mechanical energy we know that is associated with just the object is kinetic energy, K equaling 1/2 mv squared. Nothing in this equation requires anything else from another object. So if the system is just one object, really the only energy it can have is the kinetic energy of that object. Now, let's say our system is the car and the Earth, and they might phrase this as use the car-Earth system, all right? Well, now the Earth is being included. So we should include the gravitational force. Now I see this whole thing. I'm zoomed out again. And now there is gravitational potential. There's the kinetic energy of the car, 1/2 mv squared, and there's the gravitational potential, m times g times h. My computer just did something weird. Are we back? Oh man, that was odd. M times g times h. Well, the AP test likes to have, you would almost call them a trick question, where they might say, oh, use the system of the car. And then you gotta know it's just kinetic energy. Or you'll see this terminology a lot, like car-Earth system. If there's three things, the car-Earth spring system, they're really just trying to cover their bases. So they're being absolutely clear what they want you to include. On any one of my quizzes or tests, if you're unsure, you can call me over, because you can probably tell I don't always use this kind of phrasing, all right? If in doubt, just use energy conservation as normal, but you could always ask me, and I'll say, yeah, you can include the Earth in our system. But you'll see phrasing like this a lot on the AP test. Okay, those were the things I wanted to include, just additional info related to energy conservation problems, particularly how you might see them on the AP test. Thank you.